superfluous dot structures, so if you'd like to pause the video right now to record these, and then I'm going to move on to some examples. So the first example we're going to do is silicon tetrafluoride. The first step in doing dot structures correctly is to count the number of valence electrons that you're going to use in that molecule's dot structure. Silicon is placed here on the periodic table, which means that it has 4 valence electrons, similar to the group number. Fluorine is over here, which has 7 valence electrons, which again is similar to the group number. And then there are 4 fluorines, so that adds up to 28 electrons total for the fluorines, 4 for the silicon, which is 32 electrons total to place in that dot structure. The other helpful thing to do is to take the 32 electrons and divide it by 2 to get the total number of pairs of electrons, because electrons are going to be placed in pairs in these dot structures. The next step is to decide which atom would go in the center. Typically the atom that's written first, or it is the only atom in that structure, is in the center. The other way is to find the atom that has the lowest electronegativity in that structure. So silicon's here and fluorine is here, which means that the electronegativity of silicon is less than fluorine because it's lower and it's left. So silicon's going to go in the middle of this dot structure, so you just write it. And then fluorines are going to go left, right, and top and bottom. If there are 4 of them, those are the locations for this very two-dimensional shape. The next step is to bond your center atom to the outside atoms by placing a pair of electrons between them. And if I do that, my fluorines are now bonded with this model to the silicon, and it already obeys the octet rule. I'm just going to sort of cover these up with these little chips here. And the octet rule basically says that each atom wants to share 8 electrons in a dot structure. There is another rule called the Duet Rule that only applies to hydrogen, and hydrogen only wants to have 2 electrons in its dot structure. So the next thing we're going to do is take the rest of these pairs, there's 12 of them, and we're going to place those around the fluorines, and each fluorine will have 3 pairs on the outside called lone pairs, and that will add up to 16 pairs of electrons. So again, if you want to count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I have placed those 16 pairs. You can redraw this a little bit differently. You can draw this with what are called structural lines. And so instead of showing dots where the bond is between the 2 atoms, you would show that with one line if it was a single bond. So each of these lines represents 2 dots, or 2 electrons, and that is the definition of something called a single bond. The other thing you would do is still just place the lone pairs as dots around them, and so these dots that I'm placing currently right now are called lone pair or unshared pair. So if you just keep them separate, again, these outside ones are called lone pair, or some people will call them an unshared pair, or sometimes they'll even say they're unbonded. So that's the correct dot structure for silicon tetrafluoride. The next example we're going to do is going to be with selenium and oxygen, called selenium dioxide. To show you another option, you could make cards in case you don't want to erase or you think you might get the dot structure wrong. I can create just these little element cards, and then instead of using a pen or a pencil, I'm going to use these little chips as my valence electrons. So I've grabbed 6 of them for selenium right here, because selenium is going to have 6 valence electrons. It's located right here. Oxygen also has 6 valence electrons. So again, selenium has 6 valence electrons, and oxygen also has 6, but there's 2 of them. So that's going to equal 12 electrons for the oxygen, 6 for the selenium, and that's 18 electrons total. Or again, if you want to count them as pairs, I would have 9 pairs of electrons. So again, these would be, I'm just going to use a different color for the oxygen. It really does not matter whose electrons are whose when these molecules bond, but sometimes it helps to see what's going on if they're different colors. So there's 6. So again, the first step is just to bond these atoms together. So you can show them this way, or if you want to show the dots this way, and you can just move them around without erasing. I'm just going to take these two and make them a lone pair on the selenium for now because I can move them. And then oxygen most of the time has 2 pairs of lone pairs. So I'm just going to take and place those. That leaves me with these left, and I could place them on the outside, but let me show you what's wrong with this. These electrons count, these ones right here that are shared for both atoms, so that one has 8, again, that octet rule. And if I look at this oxygen, these are shared, it has 8, but currently the selenium only has 6 electrons. So again, we have to follow something called the octet rule. And right now, selenium does not have 8. So one of these oxygens is going to have to take a pair of electrons and make what's called a double bond. So I'm just going to pick this outside oxygen on this side. It very well could have been this oxygen, which will create what's called resonance. But we're going to deal with that a little later. So this is the dot structure that works. Again, that one hasn't changed. This one has moved those electrons in. And when I cover these up, these count for both. So now selenium has 8 electrons. So what I'm going to do is just redraw this with the dots included. And make it more permanent with my pen. But the benefit of those little movable chips is that you can move things around and you don't have to erase. So again, that's the valid dot structure. The other thing we could do is we could again draw these with lines. So this would be 2 lines and 2 lone pairs, and then a lone pair there and 1 line, and then this one would have 3 lone pairs. So now we have something new. We have something called a double bond. So this right here ends up turning into something called a double bond. That means that 4 electrons are shared in that bond, and they count for both atoms. So this is the dot structure that's valid for selenium. And again, the one word I talked about was a word called resonance. And resonance is not something I'm going to deal with right now, but we can deal with it later. This structure would have what's called a resonance ability to move the bonds around. All right, the last example I'm going to do with you is hypochlorous acid. So hypochlorous acid, again, what you're going to do is count the number of valence. So hydrogen has 1, it's right there. Oxygen has 6, and again, fluorine has 7. So that would add up to 14 electrons total. Or if you do the pairs, 14 divided by 2 would be 7 pairs of electrons. The next step is decide who's in the middle. In this case, hydrogen is always on the outside, and fluorine has a higher electronegativity than oxygen, so it would be on the outside, because again, it's farther right and up, right there. So this is actually written the way it's going to bond. So oxygen in the center and the fluorine and hydrogen on the outside. I have 14 pairs, so if I place them, I'm going to have, I'll put, again, 2 here to bond between the oxygen and the fluorine, 2 here to bond between there. But again, hydrogen follows the Duet rule, so that already has enough electrons. So that is only for hydrogen. That's only 2 of the 7 pairs. So I'm going to place the pairs around fluorine that's typical, which is 3 pairs. So 1, 2, 3, 4, 5. I still have 2 pairs left. So there's the 6th and the 7th pair. And again, if I kind of cover up each atom here, and I look at just my oxygen, it has 8 electrons around it. If I pull this away and look at just my fluorine, I have 8 electrons around it. Another thing that I've seen teachers do is they'll circle. So they'll circle this and say, look, there's 8 electrons around that. If you circle this one, and you again kind of ignore that part, these are those shared electrons, and that one has 8. And then again, hydrogen follows the Duet rule versus the Octet rule for these 2. And so the bond works out with all of those atoms having the satisfied dot structures. And again, if you want to use the lines, you would draw the dot structure like that. I do have 2 other examples, but I'm just going to show you the right answers for these. This is the answer for sulfur dioxide, which also would have, again, something called resonance, but I'm not showing it yet. So that's kind of a to be continued. And then this is the dot structure for water, or dihydrogen monoxide. And again, what I did was I followed these rules, and I had to use the correct number of valence electrons in those atoms.